everyone, welcome to the 3-4 Methods Revision Lecture. So today we're going to be covering most of the topics in 3-4 Methods, and we're especially going to go through some of the harder topics. So yeah, just wanted to say welcome to the lecture. This lecture is run by HR Nerds, and we've been providing a lot of really high quality free resources for students since 2007. So we have study notes, lectures, discussions, videos, newsletters, HR calculators for those of you who are interested in trying to predict your HR. We have articles, and there's a whole lot more resources that you can all access completely for free. So you can go onto hrnotes.com and register on the website. And another thing, we also have a brand new website. So this is completely new, and hopefully it's a bit easier to use than the older one. And we also have a lot of paid resources. So we have TuteSmart, which is just weekly classes where you go through the content, do practice sacks, and sort of discuss strategies for the exam and strategies to sort of learn the content. And we also have study guides. So we have the printed ones which you can order online. So I'll talk about them a little bit later. And we also have Ed Unlimited. So stay tuned, because later on I'll give you a code to get 21 days free access. Okay, so a little bit about me. So my name is Harini, and I graduated in 2020, where COVID was all the big thing. I did methods physics in year 11, so I did 3-4 methods and 3-4 physics in year 11, and the remaining 3-4 subjects in year 12. So right now I'm studying medicine in Adelaide, but before that, last year, I actually started off studying law and commerce and switched into med. Okay, so about today's lecture, we have a lot of content to get through, as is 3-4 methods, but we're going to start off with these 4 topics. So that's sort of our first area of study. We're going to talk about functions, relations, matrices, transformations, which everyone adores, logs and exponents, and circular functions, which is also loved by a lot of people. So in our second content block, we'll go through all this green stuff, so all of the calculus related stuff. And then the purple is probability. A lot of people are really scared about probability, but I find that in methods, it's not too bad, because you can do a lot of the stuff on your CAS. Okay, so straight off the bat, let's do our first poll. So I just want to ask what tech you guys use in methods. So do you guys use CAS, Mathematica, Casio, ClassPad, or any other one? So I'll just get the poll started. Here we go. So it would be great if you could all give an answer. Awesome. Oh, that's really good to know. Okay, seems like an overwhelming majority use the CAS. Okay, that's good. I also use the CAS, so I'm a little bit more familiar with that than any of the other functions. Okay, awesome, that's good. Perfect. Okay, so it seems like CAS is our majority. Towards the end, if I do get time, I have my CAS with me, so I'll start going through a bit of a few tips that you can use to work stuff out a little bit quickly. Okay, so let's get started on area of study 1. So we're going to start off with functions. We're going to talk about transformations and basically everything you need for the first area of study. And if you want, you can take note of the slides, so you'll have access to these slides. I think you should have it on the lecture page, but you'll have access to these, and you could sort of use these as a bit of a checklist on what you need to know as well. Okay, so for functions, for the first area of study, or basically for all of methods, notation is really, really important. And we need to make sure that we use the correct notation, or we will get marks taken off. So here are a few things to look out for, just straight off the bat. So brackets, big thing. So if you have trig functions or log functions, always put the brackets. So write sine bracket x. So don't just write sine x without those brackets. And make sure that your brackets have friends. Make sure it's not just one lonely bracket by itself. You want an open bracket, close bracket. And it's so shocking how many people forget to do that. Okay, and integral symbols. So think of that as sort of like a bracket because you need this open integrand to start off with, and then you need that dx at the end. So if you forget that dx, you are going to lose a mark. Okay, and tech. So obviously I will cover some CAS tips a bit later on if we get time, but just to start off, make sure that you give your answers in exact form. So unless the question specifically asks you to give it to a number of decimal places, you need to give your answer in exact form. And you should all probably know by now that your default angle should be radians. So you are going to be working with radians throughout the exam. And unless you're asked to give your answer in degrees, you will answer in radians. And lastly, don't put your CAS or whatever tech you're using, don't put that jargon into your working out. So I know like when you're solving, you might write menu algebra solve. Don't write that down as part of your working out because you're not really going to get marks for it. Okay, and a few tips for calculus. So if your function is y equals something in terms of x, then make sure you use the correct notation. So use dy dx. Don't use f dash of x. Use dy dx. If your function is f of x equals whatever in terms of x, then use f dash of x. So don't use dy dx in this second scenario. And if you're differentiating an expression, so if you're, let's say, differentiating sine of x, so you don't have y equals sine x, you just have differentiate sine x, then use d dx. So don't get that y out of nowhere. You don't have the y to start with. And a few tips for logs. Make sure that you use log ex. So make sure it's pretty clear that that e is a base. So it should be below the rest of the letters. And again, it's astounding how many people write log x. So you're not writing log, you're writing log e of x. And make sure that you're aware that log natural, so this is ln x, that means log e x, not log 10 of x. So again, something else to keep in mind. Always use brackets for log, so I've already talked about that a bit earlier, and some general tips. So if a question defines a function, so if it says f of x, then you can actually just refer to it as f of x. So let's say you have a 1 marker that's like differentiate f of x, you can just write f dash of x as the whole function. Or if it says integrate f of x, you can put the integrand f of x dx to just differentiate it. So don't waste time rewriting the whole function for every part of that question. Okay, and another tip, make sure that if you have a square root or cube root, whatever, make sure it covers everything that it needs to cover. So if it's like the whole square root of 2x plus 4, make sure it does cover the whole 2x plus 4. If it doesn't, you might be prone to making a few silly mistakes. Okay, something that some people tend to get confused with is f inverse. So f inverse is not the same as the differentiated function. So f inverse is actually not the same as f dash. So these notations are not interchangeable. And one more thing, again, people tend to make this last mistake when they're in like really high stress situations, they're really stressed out, they're rushing through the exam, and that's when these silly mistakes start to happen. So make sure that you do not, like, if you get something like 1 over x plus y, don't separate it into 1 over x plus 1 over y. That's just mathematically incorrect. So again, just like pay attention to your working out. And this is like, all of these are causes of silly mistakes. And a few tips for algebra. So where people make a lot of mistakes in algebra is with fractions and negatives. So with fractions, like I said before, people tend to do things that are mathematically not correct. And in terms of negatives, sometimes people do forget to put like a negative sign, or they forget to account for the negative in an equation. So just be a little bit mindful, work a bit more carefully when you're dealing with these in your algebra. So yeah, so here it's really easy to make silly mistakes, and that's why I'm trying to give you all of these tips to just like start off while you're still fresh to remember and maybe apply throughout today. Okay, function notation. So this is where we're getting into the content. So for function notation, it's basically in this format. So you've got, maybe I'll use a pen. So you've got f, so that's your name of the function. This is your domain. This is a codomain, so in methods, it's always going to be R, so you don't need to worry about it. This is your function and the equation of your function, and it's usually in terms of x. So here, your domain is explicitly stated. So this links to the domain. The range, so that notation doesn't give you the range, but using the equation, you can figure out what the range is. Okay, and a few exam tips for function notation. You need to be able to understand what this notation looks like and what it means. And a lot of the questions you get are in this notation. And here, just be mindful of the name of the function, so f of x. So don't suddenly get y equals whatever your equation is. So make sure you're consistent and it is f of x. And when you find the derivative, make sure it's f dash of x, not dy dx. And look at the marks to see if domain is required. So sometimes you might need to write the domain. So if you see a question that's like find the inverse, and it's a 3-marker question, that's implying that you need to find the domain. If it says find the rule of the inverse, it would usually be a 2-marker question. And that's when you don't need to find the domain, you just need to do the rule. So just look for a few nuances in the question. Okay, another one, implied domain. So hopefully this is mostly just revision from 1-2 methods. So let's say you're not given the domain. So you get a rule for, you get a relation, but they don't give you the domain. So they don't explicitly state your domain. If that's the case, you need to figure out what the domain might be. So you need to figure out your implied domain. So let's say here you've got f of x equals a divided by d of x plus g of x. First thing we know, it's divided by d of x. So something to remember is you can't divide by 0. So a divided by 0, no real solution. So that means that d of x cannot equal 0. So domain should be all your numbers except 0. Or not all real numbers, we don't know what d of x is, but domain would be d of x is not equal to 0. So you'd solve for that, you'd get a value of x that the function cannot equal. Next one is the square root one. That's also relatively common. If you have a graph like this, so you have a square root graph, you need to make sure that you're aware that the inside of your square root can't be negative, because obviously if you square root a negative number, you're not going to get a real solution. So different story for special, but for methods, if you square root a negative number, there is no real solution. So you have to make sure that anything inside the square root is positive or equal to 0. So greater than or equal to 0. So a lot of people forget that equal to 0 part. So a lot of people remember that it has to be positive, but they forget that it can also equal 0 inside the square root, because square root of 0 is still 0. Okay, next one. This is a different one. So here, you want the square root to be greater than or equal to 0, but you don't want the denominator to equal 0. So essentially, you want the square root, you want all of it to be greater than 0, but not equal to 0, because you cannot divide by 0. So I think there's an issue. These need to be swapped around here. So swap these around. Here, it's negative infinity to 0 not included, so the bottom part. And the top part is negative infinity to 0 included. So those domains need to be swapped around. So hopefully that makes sense. Again, a few exam tips when it comes to working out your implied domain. if you do not know the domain, you need to know like what assumptions to use. And these are probably the most common ones. So just keep in mind your square roots and your denominators in the fraction. So two main things to keep in mind. Okay, so let's do a practice question. Okay, so we've got square root of x equals 2 minus x, and you can work along with me, or you can try working it ahead and see if your solutions match. So you've got square root of x equals 2 minus x. And you're taking the square root, squaring both sides, and you've got x equals 2 minus x whole squared. You expand it, so make sure that you do expand it correctly. And once you expand it, this should be your equation. So x squared minus 5x plus 4. So now you've got these two brackets, and it equals 0. And we know that x equals 1 and x equals 4. So now I'm going to give you a poll. So here you've got x equals 1 and x equals 4 from our previous working. So do we include both the solutions, or do we include just one of those solutions? So I'm going to launch the poll. So let's stop this. Here we go. So let me know what solutions you get for this one. So x equals 1, x equals 4, or both x equals 1 and x equals 4. So seems like the majority are going for C, and some people are going for A. Great. So, I'll give you a bit of a clue since most people have answered. We are talking about domains. Think about whether both these solutions can fall inside the domain. So can x equals 4 fall in the domain? And can x equals 1 fall in the domain? And I want to see if anyone's changed their answers. Oh, seems like a greater proportion are going to A. Some people are doing B. Okay, so let's go through it. So here we've got the solutions. So this is our working out that we've done so far. And now we need to decide whether we're going to keep both the solutions or just pick one. So here we've got a square root, and that's where I'm a little bit wary in keeping both solutions. So I want to test out each of these solutions and see if it works out. So the actual solution is x equals 1. And we eliminate x equals 4. And that's because we test out the different values. So we sub them back in. So let's substitute x equals 1 back in here. So we've got x equals 1. So we've got square root of 1 equals 2 minus 1. That makes sense. That will give you 1. But for x equals 4, if we do square root of 4, well, that gives us 2. And 2 minus 4 is negative 2. So here, it doesn't work out. And we can't have negative 2 inside our square root. So we can say, okay, square root of 4 is equal to negative 2. But here, it doesn't work out for this because this square root cannot be negative. So this square root of x has to be greater than or equal to 0, because 2 minus x also needs to be greater than or equal to 0. So the domain of this equation is from 0 to 2 included. So that's where it's really tricky. So when it comes to square roots or numbers with a fraction and you get two solutions, just be really, really wary of whether you keep both of the solutions or pick one. And the best way is to substitute your answers. Okay, so let's keep moving. We've got sum and product functions. So sum functions, so that's basically when you're adding two different functions. And product functions, obviously, as the name implies, you're multiplying two separate functions. So let's say you've got h of x. The sum would be f of x plus g of x. So this is the sum of two functions. Product, f of x times g of x. Okay, so this might be good to keep in your band reference for reference. Domain of h of x is domain of f. So domain of the first function, intersection domain of g. So let's say g is that green line and f is that red line. Then the h would be the intersection of both of them. So it's where the domains of the two functions overlap. And another way you can sketch them is you can pick specific coordinates and add or multiply them and then join them together. So you don't actually have to work out the whole function. You can choose specific coordinates that you want to work with. Again, some exam tips for this. It's pretty unlikely to come up in the exam, and sometimes in exam 1 you might be asked to state the domain and determine the range, but again, actually sketching the sum of the functions, it's pretty unlikely to come up. Next is composite functions. So these have a higher chance of coming up on the exam, and basically they're a function inside a function. So it's like a function of a different function. So for example, h of x is f of g of x. So basically you've got f of x, which is already a function in itself, and then g of x, which is a separate function. So f of g of x is a composite function. So it's a function inside of another function. So let's say we've got domain of h. Domain of h is the same as domain of g, and that's only if the range of g is a subset of domain of f. Okay, so what that means is range of g has to be a subset of domain of f, which means that it basically has to overlap with the domain of f. Because if the range of g is all real numbers, let's say, and the domain of f is only positive numbers, it's not going to work out. It's not a subset anymore. So that's why if the range of g is a domain of f, then and only then is a domain of h the same as domain of g. So you just want to make sure that the range of the inside function fits into the domain of the outside function. Because technically, if you think about it, the range of the inside function sort of act like the x values for the outside function. Again, usually don't really work. Types of questions you might get, it might be multiple choice. They might ask you, well, are these functions compatible? Will it work? So all you have to test for is you have to make sure that the range of the inside function is a subset of the domain of the outside function. So that's probably the main thing to keep in mind. So let's do an example for composite function. So we've got f of x equals x plus 1 squared, and then g of x equals negative 3x plus 1. And the main thing I'm going to keep in mind is are the domains and ranges. So here the domain is all real numbers. Here the domain is 1 to 4 included. So we want to see if the range of this inside function, so f of g of x, so for the first one, does the range of g of x fit into the domain of f of x? And before we even do any working out, we can basically say yes, because the domain of f of x is all real numbers. We can't have a bigger domain than that. So I think, in my opinion, the best way to do it is sort of like draw a little table. Figure out your domain of f, domain of g, which you already know, and this is supposed to be a square bracket. And it might help to draw your graph. So range of f is 0 to infinity because it is a parabola. And draw your second graph, obviously restrict the domain as well. So range of your second graph is negative 3 plus 1, so it's a linear graph, and range is negative 11 to negative 2. Ooh, yeah. Range, hold up, yes. Negative 11 to negative 2. And that is our domain range of both of that graphs. So now, basically, if you want that composite function to exist, you want the range of the inside to fall into the domain of the outside, to be a subset of the domain of the outside. So if you want f of g of x to exist, we want the domain, so the range of g of x, which is negative 11 to 2, to fall into the domain of f of x, which it does. So that's why this does exist, because negative 11 to 2 falls into all real numbers. But the range of f of x for the second one is 0 to infinity, which is actually bigger than the domain of g of x. So here, the function doesn't exist unless f of x is restricted. So again, just a few things to keep in mind. Okay, so this is how f of g of x would look like. But the second one, this graph is how you need to restrict f of x for this composite function to exist. So you want that range to fit into the domain of g of x. So main takeaways here, range of inside fits into domain of outside. Okay, now let's move on to inverse function. These are a lot more prevalent in methods, so probably more important to revise these. So inverse functions are basically functions that are reflected in the line y equals x. So you can sort of imagine a function and there's like a dotted line going through y equals x. So dotted line with the equation y equals x, and you're sort of like putting a mirror over it and you're reflecting that function over the line. And essentially what you're doing is you're swapping the x and y values to find the inverse. So usually you've got y equals f of x, and now you swap it around to give x equals f of y. So you're swapping your x and y values. So really important things to take away from inverse functions is, first, domain of the inverse is the same as the range of the original function. So domain of inverse function, same as range of original. And next, range of original is same as domain of inverse. And that sort of makes sense because we're swapping the x and y value. So that's why when you swap x and y, x takes on the range, y takes it in the domain. Okay, and like I said before, the way to work out what your inverse function is, just swap your x and your y values. So that should give you y inverse, and so y inverse, so this is technically not the correct notation, this would be the correct notation, but sort of to explain what is going on. And to get your full marks, there's a pretty straightforward process that you need to follow. So you do need to give some explanation on how you're working it out. So we'll talk about it a bit later. And sometimes you might even get a multiple choice question. So you might get a graph and you might be asked, well, what is the inverse function of this? And your choices would be a series of different graphs. So let's sort of figure out how we would do the working out here. So you've got f of x is square root of x minus 2 plus 1, and it's asking you, well, what is the inverse of f of x? So first part of your working out needs to be let y equals f of x. So you can't straight away go y equals square root of x minus 2 plus 1, because it doesn't explain where you're pulling up that y from, because it's not given in your equation to start off with. So you need to sort of show that you're letting y equals f of x. So a lot of people do forget to do that. Next thing that's also really, really important is write out for inverse, swap x and y. Because if you just randomly, so if you, without doing any of this, if you just went x equals square root of y minus 2 plus 1, it's not really telling me what you're working out or what your thought process is in your working out. So this second part that you really should include is swap x and y for inverse. Last thing, so to solve for y, you basically need to say, you swap x and y. You don't really need to write solve for y. You can if you want, but essentially you're rearranging to give your equation. So now when you rearrange for the inverse equation, you got y equals x squared minus 2x plus 3. And then if you need to give the domain, you need to give it. So here it says find f inverse of x. So usually when it says find, that's a bit of a clue that it's asking you to also give the domain. So here domain is x is greater than or equal to 1, because the range of this is x is greater than or equal to 1. And then rewrite your answer. So rewrite your answer in the correct function notation. So this is how a perfect answer would look. So you've got f inverse, so you've got the name of your function, which is f inverse. You've got that domain in the correct notation, written correctly. Codomain, which is always R in methods, and then writing out your whole equation. So taking all these steps would get you all the marks for inverse. And again, I just really want to emphasize it. If it says find f inverse of x, it is always better to include the domain. If it says find the rule for f inverse of x, then don't have to. But if it just says find, do include the domain. Okay, hopefully that makes sense. So let's say you've got your inverse functions. So here, you've got a graph. You've got this purple line, which is basically y equals x. And you reflect it. So that yellow thing is a reflection of this green graph across the line y equals x. So that is your inverse function. And you might recognize it from the earlier graph. So this green thing is the original square root function we had. When we found the inverse, we got a parabola. So let's just go back really quickly. So we've got a domain from 1 to infinity. We've also got, we've got this equation of the parabola with the restricted domain, and that's what we're drawing. So that's the yellow graph here. So it definitely helps to have a bit of an idea of what some basic graphs look like. It will help sort of check your answers, see if you're on the right track. Okay, now we're moving on to transformations. So transformations are basically when you have a graph that you start off with and then you apply transformation. So you are stretching it or squeezing it or reflecting it or shifting it up and down. So those are transformations that you can apply to different graphs. So you need to know the definitions of each transformation and how you apply these transformations. Okay. So first is reflection. So instead of saying, oh, we flip the graph, we say the graph is reflected. Instead of saying we stretch the graph, we say the graph is dilated. And instead of saying, oh, we shift the graph up and down, it's a better way to say the graph is translated. But for translation, they're not too fussy. So, but especially for reflections and dilations, you want to use the correct terminology. Okay. Now let's start off with dilations. So I find that dilations are probably the most confusing. Translations, all of them, people do find a bit easier. So let's say we have a dilation by factor k from the x-axis. So you can just write dilation by factor k from the x-axis. And let's use the coordinate method. So you've got x and y to start off with, and then this is x image and y image. So dilation by factor k. So when you're talking about dilations from x-axis, we put that in front of y. So that's why people get confused. So basically, dilation by factor k, put that k in front of y, not the x. So despite it being from the x-axis, you put that from y. So basically, you have x and ky. So x image is equal to x and y image is ky. Rearrange and you've got y image is equal to y on k. So y image is y on k. So if you've got y equals f of x, you replace that with y on k equals f of x and then rearrange to get y equals k f of x. So we're going to do some examples to make it a bit more clear. Next, dilations away from the y-axis. So let's say you have dilation by factor k from y-axis, and you might have guessed it. You put that k in front of the x this time, not in front of the y. So now you've got x image is equal to kx, rearrange it, x equals x image on k, and then you replace the x with x on k. So let's say you've got y equals f of x, you replace it with x on k. So hopefully that makes sense so far. Next, we'll talk about reflections. So again, if it's a reflection in the x-axis, you put that negative sign in front of the y, not the x. And if it's a reflection in the y-axis, negative sign in front of the x, not the y. So A lot of people sometimes get confused with this. So just pay attention to where you put those reflections, where you apply those dilations in your working out. Lastly, translations. So most people find translations relatively straightforward. If it says translate k units in the positive direction of y-axis, and VCA accepts it if you write translation k units up into the positive direction of the y-axis. If you do that, it's basically y plus k. So y image equals y plus k. You rearrange, so you get y equals y image minus k, and then you replace it. So you replace the y with y minus k and rearrange. So y equals f of x plus k. And next is your horizontal translations. So this is when you've got a translation by h units in the positive direction of the x-axis, or another way you can say it is translation by h units to the right. So they also accept that. So if you want to save time, you're more than welcome to write something like that. So you've got xy, and that goes into x plus h. So x image is x plus h. So x plus h tells you translation to the right by h units. X image is x plus h, so x equals x image minus h. So it's a matter of rearranging, and then you replace the x with x minus h to get y equals f of x minus h. And keep in mind, if the h is greater or k, so translation in the y or x axis is greater than 0, it's a shift in the positive direction. So that means shift up or shift to the right. If it's less than 0, it's the opposite, shift in the negative direction, shift left or shift down. Okay, so let's continue. Let's see, we have an example here. So we've got a graph of g of x has been shifted 3 units. So shifted left 3 units. So I'm automatically going to say minus 3. Then dilated by a factor of 2 from the y-axis, okay? If g of x is log e of 3x plus 1, find f of x, the transform function. So straight away, it's telling us, well, what is the function after all these transformations have been applied? So key note here, keep in mind it's been translated first and then dilated. So that means that this transformation is affected by the dilation. So here we've got g of x plus 3, and that's equal to log e 3 times x plus 3 minus 1. So essentially, shifted left 3 units. So if you remember, straight from the start, x image equals, it's a bit hard to write it with the mouse, but that's okay, equals x minus 3. So now you've got x equals x image plus 3. So that is what we're replacing here. So we're doing x plus 3. And that's equal to log e 3 times x plus 3 minus 1. Okay, and we can evaluate that. And then dilation by factor 2 from y-axis. So basically what we have is we've got x image equals x minus 3. So that's what we already started with. And then all of this is then dilated by factor 2 from y-axis. So what's happening here is we've got x equals x plus x image onto, oh, this is terrible. Okay, I'm just going to talk through it. This is awful. It's a bit difficult to write with the mouse. Okay, so essentially you can dilate it by a factor of 2. So after all this transformation has been applied, dilated by factor of 2, so divided by 2 here. Okay, and that's basically, you apply that into the function as well, evaluate it. So you can separate it out, evaluate it, and you'll get f of x is log e 3x on 2 plus 8. So keep in mind that we're using the correct notation as well. So it's asking us to find f of x, which is the transform function. So make sure that you label it correctly and use the correct notation. Sometimes you might need to know how to transform using matrices. There are times when a question might specifically ask you to do that. But I think it's pretty easy to use matrices to do transformations. I think it's a bit more straightforward. But essentially, this a here is dilation in the y-axis by factor of a. And this b here is dilation in x-axis by factor of b. So first thing to keep note of. Next thing, the c and d, so those are your translations. So that c is translation to the left or right, so horizontal translation, and the d is translations up or down, so vertical translations. If a is less than 0, it's a reflection in the x-axis, and if b is less than 0, reflection in the y-axis. So a few things to keep in mind. So let's do a practice exam question to sort of test your knowledge. So it's asking, well, what is the transformation that maps a curve from here onto the curve that looks like this? So some people might be able to look at this and be able to figure it out straight away. Others, like me, will have to use the coordinate method. So if I didn't use the coordinate method, I would find that I make a lot of really silly mistakes. So the first thing I would do is just rearrange it so it looks a little bit more easy to sort of analyze. So you've got this minus 3 times sine, and then brackets, get the x by itself without a coefficient, plus 1. This is your horizontal translation, vertical translation. This is a reflection somewhere, and this is a dilation somewhere. So we've already recognized that, and another dilation somewhere. First, we've got dilation by 1/2 units in the x-axis. So that's what's happening here. And 3 in the y-axis. So that is what's going on here. Reflected in the x-axis. So that's this negative here. Translated 1 unit up. So that is this plus 1. And pi on 2 units left. So that is this here. And if you want to write that as a matrix, this is how it would look. So you've got 2 times x, which is a translation by 1/2 units in the x-axis, negative 3 times y, so reflection in the x-axis, and dilation of 3 in y-axis, dilation factor 3. And then translation pi on 2 to the left, and translation 1 up. So if you wanted to write a matrix, that's how your matrix would look. Okay, so hopefully that's all good so far. There are other ways to determine transformations. So if you've got let g of x is this and f of x is this, what are your set of transformations that take f of x to g of x? So your first method can be your base. So from f of x, so that's what you're starting with. Again, another mistake that a lot of people sometimes make in a rush is they might be like starting with g of x. So they might actually be testing for transformations that take you from g of x to f of x, which is not what the question is asking for. So don't waste all that time and effort. Make sure you read the question really carefully and know what it's asking for. So here you're starting with f of x and going to g of x. Dilate 3 from x. So here, that's what's happening. Dilation factor 3. So you've got 3x squared. Next, dilate 2 from y. So this is 1/2. So here we go. So you've got 3 times x on 2 whole squared. Translate 2 units to the right. So essentially, you've got 3 times x minus 2 on 2 whole squared. And you can rearrange that to look like this. And then translate 1 unit up. And now you've got your function from f of x to g of x. So this is what your matrix would look like if you use matrices. So your second method to try this out. So this is probably my favorite method, using y image and x image. I just find that much easier to sort of understand. So you rearrange them. So you've got y image is equal to this, x image is this. So rearrange to get all the x's, y's related stuff on one side and all the x on one side. So basically, now what we have is y equals 1/3 y image minus 1. So here is y equals 1/3 y image minus 1. And you've got x equals this x here. That equals x image on 2 minus 1. So rearranged, and you've got y image equals this, x image equals that. So you want to make y image and x image the subject because they tell you what transformations are going on. So here, this is what you have so far. And we'll put this in a matrix. We don't need to, but it might help if a question asks you especially. So we've got x image is and y image, and we've got that as a matrix. So 2 times x plus 2. 2 times x plus 2, 3 times y plus 1. Okay. Let me see if it should take, I think this should actually be plus 2. Oh, wait. Let me get rid of that. Okay, this is supposed to be, here, it's supposed to be 1. Let me see the previous question, yeah. So it's not 2, it's supposed to be 1. So sorry for the mistake. So we can put it in a matrix and we can describe the transformations even without the matrix. So we can say dilation by factor 3 from x-axis. Translation 1 unit up. Dilation by factor 2 from y-axis. Translation 1 unit up. Or 1 unit to the right. So you can actually write all of those things. So the next thing we're going to work on is exponentials. So this is when you have Euler's constant. So keep in mind that that letter E is not a variable, it's actually a constant, and it's equal to 2.718 and so on. It just continues. So we don't know the exact decimal. And basically, this is probably not very relevant to methods. You don't really need to know that. But what it's saying is, as n approaches infinity, 1 plus 1 on n to the power of n. So this whole Euler, the constant, approaches 1 plus 1 on n to the power of n. Again, not really relevant to methods. Okay, so here you've got your base function. So you've got f of x equals e of x. So that's probably your base function. And it has a horizontal asymptote at y equals 0. And a special property of these exponentials is the derivative of this base function is just the same as the base function. It's just e of x. So that's a special property to keep note of. So here's how the function looks. You can sort of see the dots, the dotted line here. So that's y equals 0, horizontal asymptote. A few index rules that are really good to remember. So you've got a to the power of m times a to the power of n. Well, that's equal to a to the power of m plus n. So you can add those powers. If you're dividing, then you can subtract the powers. If you are something to the power of something else, you can multiply the powers. If you want to change the base of the power, you can actually change it. So here your base is a to the power of m. If you want to change it into base e, you can do e to the power of m times log e a. So that's your change base rule, and it can be pretty useful when you're doing some working out, especially in calculus. Okay, and these types of questions do appear in exam 1, and they sort of test whether you actually know these rules and how to apply them. And big thing to know here, all of these have the same base. So these only work if the base is the same. So if I've got a, so let's say this is 2 to the power of m, and then this is 3 to the power of n, I can't make this work. So the base has to be the same for these rules to work out. So let's do another poll. Here, you guys can actually work it out and type in your answer. So I'll activate the poll. So let me stop this. Here we go. So what is your answer for this question? And you can actually type in your answers. I think you should be able to. And I know you all have a lot of questions as well, so I will get to them just before the break. So these types of questions are really, really common in exam 1. So it would be great if you took the time to work it out. I mean, I know it's a bit early in the morning in the holidays, so it's understandable if it's a bit early, it's okay. Do we have any answers? We have a few people typing. That's awesome. It is a really tricky question. Okay, awesome. We've got people typing. Brilliant. Yeah, it's really hard to type in your answers. Okay, awesome. It is hard to type. Yeah, it's hard to type your math answers, which is completely fine. Okay, so I'll start going through it. Don't stress if you haven't finished. I think it would take a really long time for all 70 people to type in their answers and for me to check each of them. So just follow along, see if you might have made any mistakes, see if it's like a silly mistake, and so on. So we've got this equation, so 3 times 16 to the power of 3x minus 1 equals 2 times 4 to the power of 3x, and that equals 0. So we did the poll, and we've got 3 times 4 squared, because 16 is equal to 4 squared. So it's always in your best interest to make it as simplified as possible. So 3 times 4 squared, 3x, minus 1 times 2. And keep in mind, so you can just leave that the same way actually, and that equals 0. So now you've got something that looks like this. You can apply your index laws, especially here. So 3x, so 4 to the power of 3x, or to the power of 2. So you can multiply those indices. Oh, what is happening here? So technically, this is supposed to be 6x. Oh, wow. So this is 4 to the power of 6x because we're multiplying those powers. Okay, wait. It's been factorized. 4 to the power of 6x. Okay, never mind. Ignore my ink. So I'll just erase all my ink. Okay, so what's happening here is they went straight from here to factorize. If it were me, I would not do that. I would actually like, I guess I could keep it like that. But essentially, it's like a quadratic that they factorize. So you can sort of think about this as a variable, just one variable, and it's like you're factorizing your quadratic. So when you factorize, you will get this. And when you rearrange, you'll get the first one equals 0, or the second one equals 0. And you only actually get one solution here. And that's because you can't get, so you can't have, hold on, 3 times 4x, 1/3. So they're getting the solution from here, but not from here. And that's because 4 to the power of 3x cannot equal -1. Anything, so if you have a positive number to any power, you can't get a negative answer. Even if I do 4 to the power of -10, it's going to be a positive fraction. It's not going to be a negative number. So that's why this second part doesn't work. So again, when it comes to exponentials and logs, paying attention to the domain is really, really important. So again, solution is coming from here. Okay, so that was about it for exponentials. let's move on to logs. Okay, just seeing how much time we have. Okay, so now we're going to move on to logarithms. So your logs are basically the inverse function of the exponent. So you have an exponential function and your log is your inverse. So that should give you a bit of an idea on what a log graph might look like. Okay, another thing, so a bit of a refresher on logs. So if you've got log base b, and so this is your base, log base, and you've got log base b, b to the power of a is equal to a. What that question is asking is, b to the power of what will give you b to the power of a. So that's what it's asking you in that scenario. Okay, and the most common log base that we would use is just the natural log, so log base e. Another way that it might be written is log natural, so ln x, but I would encourage you to just use log base e of x just because VCA also encourages that. So the exponential function has a horizontal asymptote at y equals 0. This log function has a vertical asymptote at x equals 0 because they're inverses of each other. And another thing to keep in mind, the domain of your log function is the range of the exponential function. Range of log is domain of exponential. So that's because they are inverse functions of each other. It's very likely that you'll come across questions involving logs and exponentials. Often they're interrelated. And a lot of people make mistakes with the domain of the log. So just keep in mind, the inside of this log function cannot be negative. So what's inside this bracket cannot be negative. So it's greater than 0. So it's not even equal to 0, it's greater than 0. So a few log laws. First one is if you have two logs that are being added together, you can go log a m times n. So you can actually multiply them. If you've got two logs subtracted, you can divide them. If you've got log to the power, so let's say log a m to the power of n, you can take that power, put it in the front. So multiply the log by that power. This is a good property to remember for when you're doing differentiation. And lastly, if you've got log a of x, you can change the base by using this log base rule. So all of these rules are really, really important. I'd advise you to put them in your bound reference, especially this last one, because people sometimes tend to forget about it. Okay, so that's it for logs. We might do a few exam questions based on these logs a little bit later on, but just for the sake of covering all the necessary content, let's move on to our circular functions. Again, another irrational constant that we need to know is pi, and it's irrational, goes forever, and we just use that symbol pi. And usually, especially in exam 1, you don't have to approximate your answers. You usually give your answers in terms of pi, and in exam 2, unless the question asks you to, you still give your answer in terms of pi. Okay, refresher, pi c, so that little c tells you that we're working in radians. So basically, pi radians is 180 degrees. So you need to be able to convert between degrees and radians. Sometimes it does come up. So we have three main trig functions. So we've got sine of x, cos of x, and tan of x. And keep in mind, tan of x is sine of x divided by cos of x. Okay, and really, really important to understand, sine of x and cos of x are technically the same curve. It's just that they're translations. So cos of x is a bit of a translation of sine of x. So it's possible to apply transformations to sine of x to make it into, or make it look like cos of x. Another thing that's really important is remembering your exact values. Hopefully by the time you come to the exam, you will have done enough practice so that these values just come naturally. So I was doing so much practice that I still remember my exact values. So hopefully they're just completely ingrained in your mind. So sine of 0 is 0, sine of pi on 6 is a half, sine of pi on 4 is root 212, or 1 on root 2 if it's not rationalized. Sine of pi on 3 is root 3 on 2, and sine of pi on 2 is just 1. Okay, and now cos. So if you, for some reason, forget cos, just remember it's in the opposite direction of sine. So for sine, as the angle increases, the sine of that angle also increases. But for cos, as the angle increases, the cos of that angle decreases. So here, cos of 0 is 1. So we start off with 1, then root 3 on 2, so it's going in the opposite direction of sine. Cos pi on 4, root 2 on 2. Cos of pi on 3 is a half, and cos of pi on 2 is 0. And special property for tan of x, so if you forget your tan exact values, you can do sine divided by cos. So given that you remember your sine, you're going to be able to work out every other exact value. So tan of x is 0 because 0 divided by 1. Tan of pi on 6, half divided by root 3 on 2 is 1 on root 3. Tan of pi on 4, these two values divided by each other gives you 1. Tan of pi on 3 is root 3. And tan of pi on 2, that's undefined because you can't do 1 divided by 0. So you can't divide by a negative number. Okay, so another really important property to know when you're sketching graphs are the period of the graph and the amplitudes of your graph. So for example, let's do a few general functions. So let's say we have a sine of nx, the amplitude is a, and the period is 2 pi on n. Same with the cos graph. So amplitude is a, period is 2 pi on n. The only different thing is tan. Tan is a bit different. So tan doesn't have an amplitude. If the function is not restricted, then the range is all real numbers. So it can go all the way up to positive infinity, all the way down to negative infinity. So no amplitude for tan. And period for tan is pi on n. So it's not 2 pi on n, pi on n. Okay, so let's look at how the graphs might look. So this is how your sine graph should look. So this is 0, 0. This is pi. This is 2 pi. And if it's not restricted, it just continues forever in the positive and the negative direction. The amplitude is this part. So that's one period here. Here is your range, and amplitude is half of that range value. And it's commonly a multiple choice question, so you're often given a graph and they ask you to find the equation, or they might ask you what is the range of this equation, and the range is related to your amplitude. Okay, so this is a quick crash course on the symmetry properties. So I'm not going to go through the whole unit circle because hopefully hopefully you still remember that from your 11 methods. But basically you've got sine of negative x, symmetry property, that's equal to negative sine x, cos negative x, that's positive cos of x, tan negative x, negative tan x, sine x plus pi is negative sine x. So remember what quadrants these are in. So this is quadrant 4. So quadrant 4. This is quadrant 2. What else? This is another property. So this is why I said that sine and cos functions are translations of each other. So sine of x plus pi on 2 is the same as cos of x. Cos of x plus pi on 2, same as negative sine of x. So translations of each other. Tan of x plus pi on 2, another property, that's negative 1 on tan x. I haven't really seen this one come into play that much, but this one definitely came up. And lastly, this one has definitely come up, and it's basically from Pythagoras, derived from Pythagoras. And if you've got sine squared x plus cos squared x, that's equal to 1. So all of these can be really helpful when you're solving equations. You might want to write them in your bound reference. So if you forget, you have to obviously improvise, adapt, and overcome. So think back to the unit circle. Minus x is in quadrant 4. And keep in mind, a cast. So That's basically an acronym that you can use. So cos is negative in quadrant 4, or sorry, cos is positive in quadrant 4, all are positive in quadrant 1, sine is positive in quadrant 2, tan is positive in quadrant 3, and that will help you decide which are positive, which are negative. So let's say we apply it. So given that cos A is 1/1/4, find sine of A and sine of A plus pi on 2 for all these values of A. Okay, so let's start with sine of A. So sine of A, that's equal to negative square root of 1 minus cos squared A. So you're getting that from sine squared A plus cos squared A equals 1. So you can rearrange that to get that. And the second one, you can rearrange and you can get, so the property is sine of A plus pi on 2 equals cos of A, which is just pi on 4. So keep in mind, these values, so this is negative pi on 2 to 0, so that's in quadrant 4, so that's just something to keep in mind. And when you add this pi on 2 to quadrant 4, it goes into quadrant 1. See, so quadrant 4, that's where it is, and you add this pi on 2 and it goes into quadrant 1. So that's what's happening here. You add that pi on 2 and it's the same. Okay, so I really want to go through another way you can solve this equation. So the first one, so while you are getting it from sine squared x plus cos squared x equals 1, another way you can do it, think back to the unit circle. So you can actually draw a triangle, right angle here. Horizontal is cos x, which is 1/4. Oh, no, that's not right. So let me erase that. Okay, so here our angle is A. So our angle is A. Cos of A is 1/4. So cos of A is adjacent, which is 1, and hypotenuse, which is 4. Which means, using Pythagoras, this value here is square root of 15. So that's using Pythagoras. So 4 squared plus 1 squared is 15. Sorry, 4 squared minus 1 squared is equal to 15, and that is the length of the side. Sine of A is root 15 on 4. So opposite over hypotenuse. And key thing here, keep in mind where the angle is. So it's negative here because it's in the 4th quadrant and sine is negative in the 4th quadrant. So that's just something to keep in mind. Okay. So next is solving equations. So this is pretty prevalent in methods and it can be a little bit tricky and can be a bit tedious and time consuming. So if we have a series of steps that we follow each time, it might make it a bit more systematic, a bit easier to do it. So first thing, rearrange to get a simple equation. So if you've got this, so make sure that it's rearranged. So make sure it's not sine ax plus b minus c equals 0. Make sure that it is rearranged, so you've got the sine by itself. Find your basic angle. So basically, what angle in here overall would give you c? So sine of what gives you the c value? That's your basic angle. So determine the sine of the angle. So that's what's happening here. The sine of the angle means that you need to figure out what quadrant it's in, and based on that, what sine. So if it's in the 1st quadrant, sine is positive. If it's in the 2nd quadrant, sine is positive. But if it's in quadrant 3 or quadrant 4, your angle is going to be negative. Okay, and then solve for x. And add as many periods as required. So remember, period is 2 pi divided by a. So you keep adding or subtracting periods until you fit the domain. So we'll do an example here. So we've got sine of 2 theta equals negative 1/2. So this is negative. So that tells me immediately it's in quadrant 3 and quadrant 4. Quadrant 4. So it tells me immediately that this sine value and that angle, because it's negative, is in quadrant 3 or quadrant 4. So your base angle, so B dot A, that tells me it's a base angle, and that is pi on 6, because sine of pi on 6 equals a half. And we know quadrant 3 or quadrant 4 because it's negative. Okay, next thing we know is 2 pi equals pi plus pi on 6, so this is pi here. So pi plus pi on 6 gives me the angle in this quadrant, and then 2 pi minus pi on 6, that gives me this angle here, the big one. So 2 pi equals 7 pi on 6, and then 11 pi on 6. So pi equals 7 pi on 12, 11 pi on 12, and plus or minus NP means number of periods. So how many times you want to get the period. So here we've got sort of like a general solution like thing. And here, because it's given us the domain, we can just leave our answer without this part. So we can just leave it as 7 pi on 12 and 11 pi on 12. Okay. So here the period is pi, because 2 pi divided by 2 is pi. And to fit into that domain, we can actually have more solutions. So we can actually add pi to 7 pi on 12 to get 19 pi on 12. Add pi to 11 pi on 12 to get 23 pi on 12, and that still fits into the period. So what I like to do is I like to make this 24 pi on 12, just so I know what is my highest number. So 24 pi on 12, just to know what number I can go up to. Okay, so this is another question. And I'd like you guys to have a go at this by yourself. And it's great to see so many people put answers. Ooh, and sad face and smiley face, okay? So let's get the answer. We're gonna get to the break soon. I know it's been a bit of a long time. Oop. Have I not done this poll? Poll 4. Oh, sorry, this is the wrong one. Poll 4. Here we go. So have a look at the question and you can type in your answer. So again, I'm only putting like the really hard questions on, so don't feel too unmotivated if you're not able to do it straight away. I think I might just give like 2 minutes until 10:45 to have a go at that one. Okay, we have one person typing already. Awesome. Okay, nice. It's okay, don't stress. So it's completely anonymous, so I'm not gonna know who typed the answer. No one else is gonna find out who typed what. So completely anonymous. Okay, so it seems like people are getting some relatively similar answers. Okay, so let's go through it again. Don't stress if you haven't finished it. I'm not really allocating a lot of time to get this done. So we've got sine cubed x plus cos squared x times sine x, so looking pretty horrific already. So let's try solve it. So first thing to keep note of, the domain, and we want to try rearranging it to see if we can sort of make it look a bit simpler. So first thing we know is we can factorize sine x, and then sine squared x plus cos squared x equals 0. And if you remember the property from before, sine squared x plus cos squared x is equal to 1. So now we've got a really simple looking equation. That's just sine x equals 0. So really simple this time. And x is, well, you can have x is 2 pi, 3 pi, or 4 pi, and your base angle can be 0. So period is 2 pi, base angle is 0, and you keep adding the period until you get that domain. So base angle is 0, and your other angle is negative pi. Oh wait, not negative pi, pi. So 0 and pi are your base angles, and you can keep adding until you get this. So you can see how we can rearrange it to really simplify it. So next time that you see something squared with squares or cubes in trig, see if you can simplify it. See if you can get it with sine squared x and cos squared x, and then that sort of simplifies itself. So that's just a little tip. So if x was all real numbers, so let's say the domain wasn't restricted. So let's say they didn't give us a domain to solve. They were just like solve sine cubed x plus cos squared x sine x equals 0, and that's it. If that was the case, x would be n times pi. Because we've got our first solution, so we've got 0, we've got pi, we've got 2 pi, 3 pi, and you can see that they're all multiples of pi. So it's basically n times pi, and n is a subset of z. So z is all integers, so all whole numbers, can be positive or negative. And that's your general solution. So that brings me to our next concept of general solutions. And you give these general solutions when the question doesn't specify your domain. So if the question doesn't give you a specified domain to solve for x, you'd need to give a general solution. Or if you're specifically asked for a general solution, then again, you would need to give a general solution. So when you come to f of x equals a, then you can solve. So you can say x, let's say cos of x equals a. Then you can solve. You've got 2 times n pi plus or minus cos inverse of a. So this is assuming that the pi is 2 pi. Oh, sorry, that the period is 2 pi. So that's equal to, so that's for cos of x. For tan of x, you'll notice that the period is pi, not 2 pi, because the period of tan and cos and sine are different. And that's your general format. And for sine, that is your general format. So you can see that it varies, but it's a general format, and you'll see that when you do cos inverse, you'll get some equations. So you'll get a specific value. Okay, and do not forget to write n is a subset of integers. So that's really important that you write that, otherwise you might lose a mark. Okay, so again, it can be tricky to get general solutions. So overall, trig can be a bit tricky, especially in exam 1. So try to work in steps. So first, again, rearrange to get that simple equation, find your basic angle, find the sine and what quadrant these angles are in, solve for x, and then add as many periods as required. And that's not going to happen because we don't have a required number of periods we need to add because the domain is not defined. So you add n periods, where n is a subset of integers. So let's do another example. So we've got this really messy looking equation here, and we want to solve 3 times sine of x on 2 minus 1 equals 3 on 2, and we want to solve for x. Okay, so we want to rearrange it. So we've got just this sine and that function inside it, and we've got sine of this equals a half. So now we know what to do. So our basic angle is pi on 6 or 5 pi on 6. So it's in quadrant 1 or quadrant 2 because it's positive. So now we've got x equals 2 times whatever your basic angle is. So we're rearranging it. And period is 4 pi. So we've got x equals 2 times pi on 6 plus 1 plus 4n pi, or x equals 2 times 5 pi on 6 plus 1 plus 4n pi. So basically your two solutions in your different quadrants, and you're adding 4 pi times n. So the number of period, so the size of a period times the number of the period. And don't forget, n is a subset of integers. So let's move on to sketching graphs. Here we go. So here, it's really important in exam 1, especially when you have to do your working. It's often worth a lot of marks as well. So make sure that you've sort of got the right scale, it's curved, you don't have a hairy graph. Make sure that it's not some sort of sharp, jagged line. And make sure that if there's an asymptote, make sure that you do have asymptotic behavior. So obviously you don't want the graph touching the asymptote, you don't want the graph approaching the asymptote and then suddenly realizing you don't have enough space and curving away. So make sure it's continuously approaching the asymptote and showing the right curvature. So usually the functions in exam 1 aren't too complicated, so they are definitely doable within the time. And the main thing to look out for is get the domain and pay attention to your general shape. Okay. So lots of ways to sketch, and you can use the method you're comfortable with. So you might find it more comfortable to sketch your intercept, find out all the important points, and then sketch them together. Other people might find it comfortable because they know the shape, so they sketch the shape and then label the intercepts later, so up to you. So to sketch tan, f of x equals a times tan nx plus c. Your first asymptote is at this inside equals pi on 2. And that's because tan of x is not defined, so tan of pi on 2 is undefined. So the graph isn't defined at tan of pi on 2. First x-intercept, that's when this equals 0. So obviously, you're making y equals 0, solving it, and you get nx plus c equals 0. If it helps, oh, and one more thing, point of inflection. So that's when your graph is going up, and you have this weird thing here. That's your point of inflection. I haven't drawn it perfectly. And that's halfway between the asymptotes. So that's another key tip that might be really useful. And range all of your numbers because it's from bottom to top. So unless your domain is restricted, range is all real numbers. Period is pi on n. Okay, so let's do an example. So let's have y equals tan of x minus pi, and we want to sketch it for this domain. So first we figure out the asymptotes. So we make this inside equal pi on 2. So x equals 3 pi on 2, that's where your first asymptote is. The period is pi, so asymptotes are where we add the period. So we keep adding the period until we get the whole domain and the asymptotes within that domain. So 5 pi on 2, that's outside of our domain. So our period is just, our asymptotes is just 3 pi on 2 and pi on 2. Next thing, we've got our asymptotes figured out, so we've got our first step done. Next, we can join those curves. So write out those asymptotes and join the curve. Make sure that there's a point of inflection about halfway between those asymptotes. Okay, and you can see here, don't forget to make it clear that this is a close circle. Make it really big and noticeable, close circle. And obviously, label the intercepts, the asymptotes, and the coordinates of these endpoints. So make sure you give coordinates, not just one number value. Okay, so that is the end of the first block, and it's also the biggest block. So good on you for just sitting through it and absorbing all of this information. So it's 10:54 now. Okay, so takeaways from block 1, we've already gone through that. Let's do the last poll before our break. Here we go. Oh. Great, refreshing as usual. Okay, let me see if I can find the methods poll. There we go, perfect. Poll 5. So this one is hopefully pretty straightforward. And yeah, for those of you who have answered, false is correct. So the asymptote of sine x is 2 pi and tan x is pi. So yeah, it is a false statement. So now let's head on to our break, and I will answer the question in just a minute, all the questions. Okay, so first thing I wanted to highlight is, for those of you who are interested, we have a Year 12 exam revision pass, so that's basically classes. And if you pay $379, you can basically get access to live classes, previous recordings, online tests, and basically all the resources for every single one of your Year 12 subjects. So that's just like $379. It might be really useful for you. So you can use this link to enroll if you're interested. You have access to the slides, so you can look at them later and see if you want to access the link. Another thing, if you're interested, private tutoring. So this is good if you want to have like one-on-one help with any concepts, any concepts that you're struggling with, or if you just want one-on-one help to extend yourself, private tutoring is a good way to go. If you book an info call, you can get matched up with a tutor. Okay, now let's move on to Q&A, the much awaited Q&A. So let's see. So I'll present this. Okay, here we go. So we've got a Q&A here. CAS shortcuts. Yes, I definitely will share CAS shortcuts. I'll do that toward the end of the session today if we have time. So yeah, we'll definitely do a bit later on. What are some ways I should revise for methods apart from doing practice exam? So doing practice exam is probably obviously the best way to revise for the exam. Don't make the mistake that a lot of people make. I know that many people do practice exams, cross their answers, and then just leave it at that. Make sure that the exams you do are really worthwhile. So no point in doing 20 exams and not really going through them and like learning from your mistakes. So focus more on going through your exams rather than just like mindlessly doing them, correcting them, and then just setting them aside. So I know that I spent, especially for exam 1, I spent more time going through it at the start when I was like making a lot of mistakes. So I spent more time actually going through it than actually doing the exam. So a little tip. Another tip, I didn't use this for methods when I did it in year 11, but I did use it for special in year 12 and it was really good. So this is especially for exam revision. So when you're doing these exams, have a little book to keep note of any of the errors you might be making. So that, when it comes to revision and checking your answers, you can check out, so you can look out for those errors and make sure that you don't make them again. So yeah, that's a bit of a tip. How do we set up our CAS? Yeah, I will definitely come to this. I wonder what this will do. Okay, I'll just leave this here. CAS related questions. I'll come to that toward the end. How many practice exams should we do? So this question always comes up, and my answer always changes depending on the person who's asking. So if you are very strong at methods, you're feeling confident, and you're like, I'm more strong at methods than maybe my other 3-4 subjects, obviously you would focus more time on your other subjects rather than methods. So that's a thing. Another thing, if you find that you're a bit weaker at methods, you're not as confident, and you are feeling a bit nervous for the exam, well, everyone's nervous. If you're feeling more nervous for the exam, obviously maybe do more practice exams to get a bit of a feel. As a general rule, I think doing a minimum of like at least 5 at the very minimum, exam 1 and exam 2. That might be good to get you used to it. Again, that's just my opinion. So if you ask someone else, they might give you a different answer. So again, as much as you think you need, if you're doing exams and you're like, I'm getting all of these right, there's no point in doing them, then don't. If you're limited on time, do questions that you find hard. So time yourself to do hard questions instead of doing the easy questions that you are already confident with. So you don't have to do whole exams. You can just do ones that you need to work on. Can we define a function if we want to? Yes, so you can. Yeah. So you can say let y equals h of x, and then, yeah, you can refer to it as h of x for the rest of the question. So as long as you actually define it at the start, yes, you can do that. Would you suggest writing your working out in headings? So, okay, let y equals f of x. So I'm assuming that is also related to defining the equation. If you mean in headings, I think, so you should put your working out in the lines they give. Don't put them in like the question space or something, because the examiners might miss them. So put them in like the lines they give for your working out. So I hope that answers your question. But yeah, you can define your equation. So you can say let y equals f of x and refer to it like that. Currently, oh, okay. So, you are working ahead. That's awesome. If you're in Year 11 methods, so a lot of the Year 11 content forms the basis for Year 12. So everything you learn in Year 11, literally everything, you build on in Year 12. So instead of like trying to work ahead on the Year 12 content, I would make sure that you're like just very, very confident in the Year 11 topics. And when you are, then you'll be able to go to Year 12. So during the holidays, maybe revise your Year 11 content so that you don't forget all of it, and that will help you prep for Year 12. Okay, how many practice exams? So I have answered that question. Look, ideally you want to get all of them done, but there are sometimes questions that really stump you. So you don't want to waste time focusing on that. So during the exam, focus on your strengths. Do all the questions you can. If there are questions you can't do, obviously, just leave them, come back. If it's multiple choice, guess. Put a little bit of working out. So if you're like absolutely stumped, have no idea how to do that question, put some form of working out. You could at least get 1 mark out of 3. So that's what I would advise. But hopefully you are able to do all of the questions. If you do like enough practice exams, so if you do some practice exams, you'll start to get a feel of how the questions are like. For example, the exam 1 for methods for I think the past 10 years, it always starts off with a differentiation question. It always says differentiate a particular equation. So yeah. How do we restrict the domain? Restricting the domain. So if basically the point of restricting the domain is usually to make it a one-to-one function, so that you can actually have an inverse. So that's one reason. And another reason we restrict the domain is to make sure that, the function actually works. So for example, if you have an inverse, the implied domain, we don't even restrict it. The implied domain is that if you have a log function, the implied domain is x is greater than 0. So that's something to keep in mind. And we restrict it by just looking at the graph and selecting x values that suit whatever we need to do. So if we need to make the function one-to-one, looking at the graph, how can we make it one-to-one? Okay. No bound reference in exam 1. What info is most important to memorize? Okay, so exam 1, yes, no bound reference, but keep in mind you have access to the formula sheet. So you can use that formula sheet to work on, to sort of like guide you. So there's a lot of information on calculus in there. There's a lot of information on probability. You know what, I'll get that up for you. Methods, formula sheet. Here we go. So you can see there's a lot of areas, volumes, and all of that. If you ever forget, there's all these formulas for calculus, so you don't actually have to really remember anything. Probability, they still give you the addition rule, they give you conditional probability, so they're basically giving you a lot of the stuff you need to. So if you're ever like, I'm not sure how to do it, you can actually refer to the formula sheet and you'll be fine. Okay, It's 11:05. I will come back to these questions again. So for this last question, example of differentiating, we're going to be doing calculus soon, so we will come to that soon. Okay. So we've done a bit of Q&A. Don't worry if I haven't answered your question. I will definitely come back to it towards the end in the next break. So right now, let's have a break. It's 11:05. I think we can do a break until about 5 minutes. So sorry the break isn't too long, but take 5 minutes to have a drink, stretch, and come back at 11:10. So see you all a little bit later. Okay, welcome back from the break. Let's go through our next content block. So before we do so, I just want to let you know about this resource called Ed Unlimited. I really do recommend it. Not because I'm like biased or anything, but because I did use it when I was in year 12, and it was June 2020 as well. But basically, it's like, you could sort of call it like a Netflix for all your VCE resources. So you have, like study guides, topic tests, if you're doing English analyses of like different texts. So all of that, and it's just really useful just because you have all of this in one place. You can literally access it anywhere. So yeah, it's a great resource. If you use this code, so Harini VCE, you can actually get it free for 21 days. So even if you decide, you don't want to buy it, I do recommend that you try it out for the 21 days, see if it's something that you're interested in. So no harm in trying it out. But yeah, definitely recommend trying to use this. So next one, so this is your bookshop offer. And if you use the code 15SEP, you can get 15% off on your physical books. So you can just go onto the HR Notes online shop and you can shop for anything that you might need. And using this code will get you a 15% discount. Okay, now we're moving on to calculus. So I just want to see how you feel about calculus. So on a scale of 1 to 10, what is your feeling about calculus? So let me just get that poll up. Here we go. So how do you feel about calculus on a scale of 1 to 10? Would be interesting to see if it was someone's reason for choosing methods. Oh, okay. So we have some people who chose methods because of calculus. Lovely. Okay, great. So I feel like most people are on the confidence side. I know that, it differs. So, some people have calculus as their strength, others have it as a bit of their weakness. So yeah, we've got a pretty good mix. Ooh. Okay. So, but it's nice to hear calculus brings some of you a lot of joy. Okay, so let's actually head straight into calculus. We're going to talk about differentiation. So in the poll, a lot of people were asking if I could do some differentiation, do some examples of that. So that's what we're going to do now. We're also going to do integration, which is the opposite of differentiation. And we're going to go slightly into probability. So firstly, the derivative. So differentiation is, forget about the whole machine thing. It's basically, it helps us find the rate of change of a function. So how quickly is a function increasing or decreasing, or is a function flat? So that's what differentiation tells us. The first thing you need to know is differentiation by first principles, and that is looking like this. So it looks pretty gross, but what's happening here is we're saying as h approaches 0, so as h approaches 0, this limit approaches that derivative. So basically, I know we can't actually make h equals 0 because it's a denominator, but as it approaches 0, we get that derivative function. And we'll do an example of this soon. And it also tells us how we can find out the change in y based on what x is. So depending on the x value, we can actually figure out how y is changing in relation to it. And this is called instantaneous rate of change. So it's rate of change at that very instant. So again, when you're doing differentiation, I did sort of touch on it a bit earlier, but when you're doing differentiation, make sure that you use the correct notation. So if your original function is f of x, the derivative is f dash of x. And the derivative at a certain point is f dash of a. So if a point was x equals a, the derivative would be f dash of a. Our next type of notation is Leibniz. I don't even know how to say this, but you don't need to know the name, but this second type of notation. So you use that if you get y equals something in terms of x, and the derivative notation is dy by dx. So that d basically stands for change in. So change in y divided by change in x. And if x equals a, then the way you write this is at x equals a, dy dx equals whatever your value is. So here are some basic derivatives. You don't really need to memorize them because the methods formula sheet has all of these written down anyway. So no need to memorize all these derivatives. So here for these derivatives, you've got f of x, f dash of x. So original function on the left side, derivative function on the right side. So first we've got x to the power of n. That's probably the most common one, and that's n. So times by the power, and then subtract 1 from the original power. So that's basically the way to work it out. Times by the power, subtract 1 from the power. If you've got the power rule, so you get this a here and put it here, n times by the power here, then keep the same thing inside the bracket, power minus 1. So same principle going on. And the rest of these you can find in the formula sheet. So the derivative of an exponential with the log base e. So it has to be log base e. That is a times e to the power of ax. And this might be good to have in your formula sheet if you want. So derivative times original. Here for log e of x, derivative is just 1 on x. This might be good to have in your formula sheet though, the second part. So it sort of gives you a bit of a general rule, but again, everything that you need is on the formula sheet, so if you ever forget it, you don't need to stress out. So let's do some basic derivatives. So let's go y equals e to the power of 4x squared, and it wants us to find dy dx. So dy dx, well, that is the derivative of what's of the power up here. So derivative of this times e to the power of 4x squared. So derivative of the power times just the original. Derivative of the power, well, you've got 4. Take the 2 and times it in the front, so 4 times 2, x to the power of 2 minus 1 is 1, so x. So we've got 8x e to the power of 4x squared. So these types of questions have literally appeared on exam 1 every single year. So for the past 10 years, they've been coming up on exam 1. So you need to be really familiar and really comfortable with applying your differentiation. So I can guarantee, well, I can't guarantee, but I am pretty certain that they are going to come up in this year's exam as well. Okay, so different rules. So these are some, I guess, rules that might help you find the derivative in some circumstances. So let's say you've got the function inside a function. So if you've got a composite function, the derivative of a composite function is derivative of the outside function times, with the inside function the same, derivative of the inside function. So it's easier to look at this. So this is the chain rule. So dy dx is dy du times du dx. So we use the chain rule. It's also on the formula sheet, and I'll give you an example of how we use all these rules soon. Next is your product rule. So you have two functions multiplied by each other. So first you derive the second function, keep the first the same, derive the first function, keep the second the same. And that's what's happening on the right side as well. And lastly, quotient rule. So that's when you have divisions with functions. What you do, derive the first function, keep the second the same, derive the second function, keep the first the same. Remember, it's subtraction here, and then divided by bottom function squared. And same thing is happening here. So you'll have all of this on your formula sheet. And it's a really common exam 1 question, especially if you have something with the quotient rule, usually worth 4 marks or 3 marks. And you need to apply the rules, show your substitution, and give your final answer. Next types of questions that we get are tangents. So tangent, so if you have a tangent to a function, it's basically a line that shares a common point and gradient at that particular point. So basically, if you've got y equals f of x, then the tangent at x equals a is at f dash of a x minus a plus f of a. So I know this sounds really confusing, but I'll explain through it. So basically, to find the tangent, you need to know the gradient of a curve. So let's say you have a parabola and you want to find the tangent at x equals a. You differentiate that parabola and you get the equation for the gradient. You substitute in a wherever x is, so x equals a. You substitute that in, so you've got f dash of a, that is your gradient. So f dash of a is your gradient, so that's the gradient of the tangent and the gradient of the curve at that point. So we've got the gradient, so now the equation of the tangent is y equals mx plus c. Oh gosh, this just gets worse. Mx plus c. Another thing you know is a coordinate on the graph that the tangent is intersecting. So y equals mx plus c, you know what m is, and to find out what c is, you know a coordinate, you just substitute, like your general linear equations. So you're just going to substitute a and f of a. Normal, so normal line is basically perpendicular to the tangent. So if a normal line and the tangent line intersect each other, they are going to be perpendicular at right angles to each other at that point. So again, if we have y equals f of x, we know the gradient of the tangent. The gradient of the normal is -1 on gradient of the tangent. So if you remember, perpendicular lines, so m perpendicular equals m, oh wait, not m, so 1 over, so -1 over original m. So same principle applied here. So normal and tangent are perpendicular. So you find the gradient of your tangent and then you find the perpendicular line. So we'll do an example now. So it's asking us find the tangent and normal to this equation at x equals 1. I think probably the easiest way might be to expand that equation. Oh, wow, hasn't shown the derivative or how that comes about. Okay, derivative. So if I was doing this question, I would expand it. So it's going to be a cubic. Expand this equation, find the derivative. When you find the derivative, sub in f of 1. So f of 1, should equal -1. So f of 1 is -1, so the gradient of your tangent is -1. Then substitute the coordinates. So at x equals 1, f of x equals, let's see, 1 minus 2 is -1, -2, 1. So 1 times -1 times -2, so that's 2. So our coordinate is 1 and 2. So we substitute that coordinate to get this 3. Again, gradient of the normal is 1 on, so -1 on gradient of the tangent. So -1 on 1, so the gradient of the normal is +1 here. So you can see here, it sort of shows how it looks in the graph. So that red line is the tangent, and you can see the normal is perpendicular, and you can see that it's right angle to each other. Okay, so that's about it for tangent and normal, and I'll probably give you some shortcuts. Actually, I'll give that to you right now. So if you have your CAS, if you have it with you, the shortcut to find the gradient, so the tangent line, is you go menu, calculus, and then the number 9, so tangent line. So menu, calculus, tangent line. And you write in the equation, so you write in x times x minus 2 times x minus 3, comma, x equals 1. And that will give you your equation of the tangent line. And that's all you need to do. And same with normal. So if you go menu, calculus, normal line. So just below the tangent line, there's also a function to find your normal line. So same principle, and that will help you find the normal at that point. So I hope that helps with the calculus, with the CAS, so you don't have to go through all of that working out. Next is rates of change. So let's say you have y equals f of x, and you're like, what is the instantaneous rate of change at x equals a? So again, instantaneous rate of change, the exact rate of change at that exact point. So for f dash of a, so first you find the derivative, so you find f dash of x, substitute a, so now you get f dash of a, and that's the instantaneous rate of change. But there's a difference. There's also average rate of change, and you calculate that when you have two separate points. So for example here, if you have x equals a and x equals b, you calculate average rate of change by going f of b minus f of a divided by b minus a. And that would give you your average rate of change. And this might look familiar because it's the same as your formula for gradient. So y2 minus y1 divided by x2 minus x1. So that's your average rate of change. So essentially you have 2 points and you sort of imagine a line connecting those 2 points and you're finding the gradient of the line. So often they can appear together. So important that you don't confuse instantaneous versus average. So instantaneous, you only have 1 point. Average, you have 2 points. So that's how you would distinguish them. Next, a really important point is stationary points. So these occur at x equals a if the derivative is equal to 0. So for example, here, local minimum, the derivative here, the instantaneous rate of change would be 0 here. Even here, instantaneous rate of change is 0. So I'm drawing the tangents pretty terribly, but hopefully you get the idea. And instantaneous rate of change is 0. And an important point that I want to make here is with the points of inflection. So not all points of inflection are stationary. So you actually need to test out and see if the derivative is equal to 0 at that point. And again, stationary points, as the name suggests, tells us the graph is stationary at that point. So basically, the graph isn't increasing, it's not decreasing, it's momentarily just flat. So absolute minimum. So again, this concept is not essentially necessary, but what it's telling you is if there's a stationary point at x equals a, then basically, if it's an absolute maximum, so it will look like this. So it's a, and here is f of b, f of b. It could be anywhere. So this is a, the stationary point, and this can be b. So at any point, f of a is bigger than f of b. That's what it's telling you. Same with absolute minimum. So that's here, it's like this. Let's say this is a. At any other point on the graph is higher than this absolute minimum. So that's an example. So this is a local maximum, and this is a local minimum. Okay. Next, we've already gone through that. Okay, so next thing, absolute maximum and minimum, always at the stationary point or at an endpoint. So keep that in mind. So there's a difference between saying local minimum and maximum and absolute minimum and maximum. So if I have a parabola, or let's say I have a cubic like this. So let's say I have this cubic. So domain is unrestricted, it goes up, goes down forever. This is the local maximum. This is the local minimum. But it's not the absolute maximum. So at this point, even though it's the local maximum, it's not the absolute maximum. The absolute maximum is here, positive infinity, because it goes forever. This is the local minimum, but it's not the absolute minimum because the absolute minimum is here, goes to negative infinity forever. So let's do an example. So we've got this function and it wants us to find the range of f. So we're sort of mixing up calculus with the first area of study now. So find the range of f. So I think a good way to do it is, because it's a parabola, you can sort of visualize the graph. So this is how your graph looks. Turning point is 0, 1. And it's from -2 to 3. So -2 is here, 3 is here. So you can do it just by drawing the graph. Or you can find the derivative and figure it out from there. So first, we know that it's a positive parabola. So the turning point is the absolute minimum. So when x is 0, the derivative is also equal to 0, which tells us we have a stationary point and it's the absolute minimum because we know how the parabola looks. Okay, so stationary point is at, so you substitute that 0 into the original function, f of 0 equals 1, and so the absolute minimum y value is 1. The maximum y value could be at -2, or it could be at 3. So obviously it's at 3, the value is bigger. So the range is from 1 to 10. 1 is included because it's part of that turning point. 10 is not included because there's a closed bracket here. It's an open circle. Okay, so you can do it that way using calculus, or you can just draw the graph and sort of figure out how it might look. Okay, so that's it for derivatives. Let's move on to our antiderivatives. So this is the opposite of differentiation, and basically the main reason we do it is it helps us find the area under a graph. So you've got this integral, you've got d dx, f of x dx, that's equal to f of x plus c. So here, the important things to note is that integrand, that dx, and this plus c that people always tend to forget. So do not forget to put that plus c at the end. So the reason we have the plus c. So let's say we have 2x. The derivative of 2x is just 2. Derivative of 2x plus 1 is also 2. So antiderivative of 2 should be 2x, but you have to have that plus c, because when you derive, you're losing some of that information. So if you have a constant in the original function, you're losing that information. So that's why it's really important to have that plus c. Okay, let's keep going. So basically, if you have any function, the definite integral will give you your signed area enclosed by the function and the x-axis. So here we go. This is our purple area, it's our signed area, and solving this definite integral will give you the area under the graph. So b is the upper bound, which is here, a is lower bound. From b to a, or from a to b, what is the area? That is how you would figure it out. You would integrate it and then substitute the b, substitute the a, and then subtract the values from each other. Again, some basic antiderivatives to keep note of. Pretty sure all of these are on the formula sheet, so again, don't stress too much about memorizing them for now. I won't linger too long on this. A few rules for integration. So if you've got a to a, sorry. So let's say you've got a to a and you want to find the antiderivative. Keep in mind, for a definite integral, you find the antiderivative, substitute upper bound and lower bound, and subtract them from each other. So when you substitute and subtract, it gives you 0 anyway. Next one, if you have a constant inside here, so basically a multiple of f of x, that's okay, you can take it out if that makes it easier for you to derive. Next thing, if you have b, a, f of x dx, you can swap the a and b, but you just want to give that negative sign if you swap them around. So often these come up in the multiple choice section of exam 2. So you just need to be aware of these properties of integration. Okay, now let's go on to the area between two curves. So if you have two curves and you're asked to find the area is given by upper bound, lower bound, f of x minus g of x dx. And here, f of x is the top curve, g of x is the bottom curve. Okay, so just make sure that you remember which is on top, which is on the bottom. In exam 1, you might get simple areas, so areas with like a bit more simple equations. But in exam 2, you might get some really complex ones, but luckily you have your CAS to work all of that out. Okay, so first things first, let f of x is this. So we'll do a bit of an example. So we have two curves. So f of x and g of x, find the shaded area. So first you need to find this area, then this area. So first we need to see where they intersect. So we need to see that intersection point for upper bound and lower bounds. So here your upper bound is 3/4, lower bound is 0. We don't really care about this intersection point here. So the first area, so this is area 1. So the first area is from 3/4 to 0, f of x minus g of x, because f of x is on top at that point. The second area is this. So the second area is from 1 to 3. 3 is upper bound, 1 is lower bound. And we're sort of taking this x-axis as y equals 0. So that's why we're doing 0 minus f of x dx. Because if we didn't do this part, if we just left it as positive f of x, we're going to get a negative area. And it's just, we can't get a negative value for area. That's just logically not possible. So then you can add the areas together and you can get this value. So you would leave your answer as a fraction unless the question tells you to give it as a decimal. So that's really important to keep in mind. As always, biggest takeaway from here, upper function minus lower function. Okay, so next poll, I've sort of answered this. If I'm getting a negative value for my integral, can I leave it like that? So if I'm calculating area and I get a negative value, can I just leave it like that? Here we go. So try this one out. So hopefully this is straightforward. Nice. Great job, guys. So absolutely correct. You want your area to be positive because you logically just cannot have a negative area. So well done. Okay, so we'll keep moving from area. We're going to go to average value now. And I'm just a little bit mindful of the time because I do want to have time to answer all your questions. So average value, basically, what is the average value of that function tells you what is sort of like the middle value. So the middle sort of y value. So it's basically the area divided by the length of the curve. And you calculate it. So I think you would need to remember this function if I'm not mistaken. Let me just have a look. Average value. Yes, you would need to remember your average value of a function. Okay, so that's something you would probably have written in your formula sheet. Don't forget, you would have to remember this one. Okay, so remember the average value is basically the area divided by length. So here, this integral tells you the area. This is the length of like the curve. So upper bound minus lower bound. Okay, so an example here, if you've got f of x, average value is this area. So first you calculate your area and b minus a is your length. Okay, fundamental theorem of calculus. So this is probably the biggest thing to know, and hopefully from all the work you've done this year, hopefully this looks pretty familiar. So if you go from b to a, and you want to integrate it, you would integrate it, have these square brackets, BA, and then substitute, subtract. So applied in every integration scenario, and it's also been coming up pretty frequently in the exam. So just make sure that this is your process of working out. Okay, let's do an example now. So let this equals 5. What is 1 to 0 f of 5x dx? So these types of questions are pretty common in the multiple choice of exam 1. So from 0 to 5, f of x dx, well, that is f of 5 minus f of 0, which equals 5. From 0 to 1, f of 5x dx, that's 1/5 f of 5 minus f of 0. So this 5x, dilation by 1/5 in y-axis. So that's why we do 1/5 f of 5 minus f of 0, and that's equal to 1/5 of 5, which is 1. And something to keep in mind, you can see that the upper bound and lower bound have also changed. So 1/5 of 0 is just 0, 1/5 of 5 is 1. So if you're not sure what this transformation means, have a look at the upper bound and lower bound and see what's happening to them. Okay, now let's move on to probability. So probability, basically the chance that an event occurs. And the way you calculate it is number of successes, so number of times it's successful divided by the total number of events that could possibly happen. And next one, probability x, the big X equals little x, so that's the number of little x's divided by the total number of events. So another way that you can think about probability is the ratio of favorable outcomes to the total number of outcomes. Okay, let's just see how you feel about probability. I just want to see if it's the same throughout for everyone. Okay, that looks pretty good. Yeah. Oh. Okay, seems like most people are okay with it or they'd rather not do it. Okay, most people are now, they'd rather not do it. Definitely understandable because probability can be a little bit hard to get your head around. Okay. Here, you've got 4 different probability rules that are basically your foundations. This is in the formula sheet, this is in the formula sheet, and all of these are logical. Okay, so first rule here is your probability has to be between 0 and 1. So when you're working out and you get a probability of, let's say, 10, you know that you've probably done something wrong. The second rule is all your probabilities of every single event should add up to 1. So again, if you add up your probabilities and you get 3, again, another sign that you are doing something. Conditional probability, so we'll go through that in a bit more depth later, and addition rule. So to find the union, you need to add each of the individual probabilities, subtract the intersection. Okay, probability distribution. That's basically a list of every possible outcome and their probability of each outcome. And we usually denote them with capital letters. So usually it's just x, and each possibility is little x here. And basically, when you add up all of these possibilities, it should be, so when you add up all these probabilities, they should equal 1. So again, probabilities between 0 and 1, sum of probabilities equals 1. Okay, intersection, that's basically where 2 elements just overlap, so there's something common between both of them. So if you have A intersection B, that's that green bit here, where they overlap. Okay, quick test of knowledge. So this is our second last poll for today. I talked about the addition rule earlier. Let's see if you still remember it. So which of these is the addition rule? Oh wow, okay, this is not very good. Let's forget about the poll. I wonder why it's not showing the A. It's all good, don't worry about the poll, guys. Okay, so the correct answer here is this one, answer A. Okay, so now let's talk about union. So it's an event or events that exist in one. So if you are talking about A union B, it's present in A, or it's present in B, or it's present in both of them. And that is your addition rule. It gives you a way to find your probability of A union B. And the yellow, green, and blue part gives you A union B. So now let's talk about conditional probability, which is a bit more common. Basically, it's when, so let's forget about this one. We don't want this one right now. Conditional probability is basically what is the probability of something happening given that something else already happened. So an example is if I have a deck of cards, what's the probability of picking a spade? That would be a quarter. But let's say I put a condition to that. If I have a deck of cards, what's the probability? So if I have a deck of cards and I pick out a black card, so a color that's black, what is the probability that card is a spade? Now it's a half. So based on the condition, your probability might change. And that's the rule. So the probability of A given B. So the probability of A happening given that B has already happened is the intersection divided by the probability of B. Next is independence. So if two events are independent, it means that the different variables don't affect each other. So probability of A given B is still probability of A. So just because B happened doesn't affect whether A is going to happen or not. So an example of that is tossing a coin. So if I tossed a head the first time, it's not really going to affect whether I toss a head or tail the second time. Another thing we can deduce is probability of A intersection B is probability of A times probability of B. Okay. And last thing that you would need to know is mutual exclusivity. And again, didn't really come up in the exams before that I know of. But when two events are mutually exclusive, it means that they don't have an overlap. They have nothing in common. So essentially, no intersection. So for mutually exclusive events, probability of A union B is just probability of A plus probability of B, and the intersection doesn't exist. So don't confuse mutually exclusive with independent. Independent is they don't affect each other, but mutually exclusive is there are no common events between them. So just keep that in mind. So that's it for block 2. We're not going to have a break. I do want to get time to answer all your questions. So now let's go on to probability. So let's start with binomial distribution. So binomial distribution basically means that there's a certain number of trials, which we write as n. There are 2 outcomes for each trial, success or failure. So is that good or bad? Success or failed. So 2 possible outcomes, and the probability of success is p. So make sure you define your distribution, and this is how you would define it. So x is binomially distributed with n trials, and p being the probability of success. And if you use x, make sure that you use that throughout your working. So don't suddenly switch to w. Keep that letter consistent. Okay, binomial formula. I haven't really seen this thing come up in exam 1. Basically, it's combinations. So you've got n trials, choose x successes, times the probability times the number of successes, times 1 minus, so times the number of failures. So again, you can have this noted down if you want, but I haven't really seen it come up on the exam. But you need to be familiar, or again, combinations formula. You'll have access to the slides, so don't stress if you don't have time to write everything down. So an example. So Shania does her homework, 25 chance that she will need help. She does homework every weeknight for 1 hour at a time. So what's the probability that she doesn't need help a single time from Monday to Sunday? So I don't think I'll do the poll here. So you've got x, it's binomially distributed, 5 trials because you're testing 5 different days. So Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Oh, I wonder why they did 5. Oh, weeknight. So weeknight is the keyword. So 5 weeknights. And the probability that she does need help is 25%. And we're saying that's the probability of, I guess, success. We can use that formula from before to figure it out, but I will show you how to do this on your CAS. 1 on 4, probability of success, probability of failure, and that should give you Let's keep working out. 5, 4. Okay, that's what the original thing is. And it's asking what's the probability she won't need help. So it will basically be probability of that 1 minus that. So 3/4 to the power of 5, you can just leave it like that. If you have, let's say, something that's binomially distributed, 3 trials and 1/4 probability of success, this is asking you what's the probability of succeeding 3 times given that you already succeeded greater than 1 times, greater than or equal to 1 time. So that's probability x equals 3 divided by probability x is greater than or equal to 1. You calculate first x equals 3, so you do it in parts. And that's this. And x is greater than or equal to 1, so I would do that on your calculator. So if you get your calculator out, again, so you can go menu, actions, menu, probability, distributions, and then all the way down, binomial PDF. So you get binomial PDF, and you'll get something that looks like this, if you can see it. So binomial PDF, so n is 3, p is 1/4, and x value is 3. And enter, and it'll only give you a decimal place, so it's not going to give you an exact answer. To find the second part, to find the probability x is greater than or equal to 1, you go menu, probability again, go all the way down to distributions, all the way down to binomial CDF. Number of trials, so it'll come up with something like this. Number of trials is 3 again. Probability of success is 0.25. Lower bound is 1. Upper bound is 3 because that's the maximum number of trials. Okay, and there we go. So we've got our answer here, and it will give it to you as a decimal point. So that's how you would do it on your CAS. So again, since we're a bit tight on time, we won't do the poll. If you're doing it on the CAS and it's a specific x value, you use binomial PDF. If it's a range of x values, so if it gives you greater than or less than or greater than or equal to, you use CDF. Okay, so those are the ways you do it. So again, shows you how to do it on the CAS. So x equals binomial, 4 trials, probability of success, and it's basically asking you what is the probability you succeed twice. So again, you go on binomial PDF, number of trials is 4, p is 0.703, x value is 2, and it will give you this answer. So when you have the CAS, it's relatively easy to work out these probabilities. Let's keep going. Binomial CDF. So that's when you have a range of values. For example, x is greater than 2. And it gets a bit tricky if it's greater than and not greater than or equal to. So you go on binomial CDF, same thing as before, number of trials is 4, probability of success is 0.703. But the lower bound is 3, not 2, and that's because the 2 is not included. So you can't succeed 2.5 times. You succeed 2 times, you can succeed 3 times, but not really anything in between. So that's why the upper bound is 3. So if you succeed more than 2 times, it means you succeed greater than or equal to 3 times. So it has to be greater than or equal to. Upper bound is 4 because that's the maximum number of trials. And that will give you this straight away. So usually in exam 2, that's basically how you do these, and usually they're just 1-mark questions. And if they're 2-mark questions, this is the working out that you need to give, plus the answer, which is your other mark. So quick exam from Vika. So this is from 2019. So each year there's a study, 36 butterflies, wingspan greater than this, okay. So we know it's binomially distributed, 36 different butterflies. The probability is greater than that is this much. So for it to be very large, we do that, binomial CDF, and you just solve it on the CAS, and you will get this answer. So sorry I'm rushing through these. I do want to have time to answer the questions as well. The second one, so that n or more butterflies in the sample are very large is less than 1. What is the smallest value of n? So basically, if the probability of x greater than or equal to n is less than 0.01, you can do trial and error, and you need to substitute the different values of n. So that's probably the only way to do it in this scenario. Okay, next, expected value. So that's your average. It's your mean. And basically, it's a multiple of the probability of successes and the number of trials. So if you've got expected value, it's number of trials times the probability of success. And usually binomial questions are relatively hard because they often disguise them. So they word them a bit strange. But you need to understand that it's all about number of successes, number of failures, and number of trials. And those are the main things that you need to look out for. Variance. So again, it's a measure of spread. So how spread out is your data? And variance is standard deviation squared. So this little symbol here is standard deviation, and that squared is variance. Again, I'm pretty sure this is on your formula sheet. This is expected value times 1 minus p. So 1 minus the probability of success. So standard deviation, square root of variance. Okay, normal distribution. So this is a specific type of probability, and basically defined over all real values. So the domain of a normal distribution is all real values. And that mean is the same as the median, which is the same as the mode. So if you want to say something is normally distributed, you can say x is normally distributed, mean is this, and this is the variance. So make sure you write the variance and not the standard deviation. So normal distribution is a bell curve. So this is how it looks, and approximately 68% of the data is within 1 standard deviation of the mean. Approximately 95% is within 2 standard deviations, and approximately 99.7% is within 3 standard deviations of the mean. Okay, so that's called the standard normal distribution, and basically there the mean was 0 and the standard deviation was just 1. And we can standardize them. So essentially, you just substitute values here. So x minus mean divided by standard deviation. And it tells you the number of standard deviations that this x value lies from the mean. So that's it for normal. People usually find normal much easier than binomial. So a few exam tips. So make sure that you use reading time effectively, plan out your strategies, look for questions that you can do, look for what you're confident in, make sure you're not missing any pages. So check the page numbers, make sure you read every page and you know what's coming up. So pick your easy questions, carefully read your long questions. So if you've got long worded questions, just use the reading time to just slowly try to understand what is being asked. During the exam, so it's up to you how you do it. So you can start with questions you already know how to do, or you can just do it one by one, but up to you. But don't always think that you're going to use your notes. So don't go into the exam and be like, it's okay if I forget this because I have my notes. Try to avoid using your notes. Okay, so that's all for the lecture. And we might need to go a tiny bit over time so I get to answer your questions. So let's go to the Q&A. So set up our CAS, make it most optimal. So I've been getting quite a few questions in that. So here I've got my CAS. So what I like to do, I didn't do this in year 11 because I didn't know about this, but I like to go Control and then the up arrow button here, and it'll show you all the pages here. So problem 1. So then I can go Menu and I can say Insert Problem. So that allows me to have different pages for each question, especially in exam 2. So exam 2 has about 5 questions, so that if I define a function, I don't have to keep erasing it. And I can just sort of flip between the different problems to sort of get the function. So that's a really helpful tip. Another thing you can do is define your functions. If you have a really long question in exam 2, obviously define the functions so that you don't have to spend as long to type it out. So if you're not sure how to define it, you go into calculator. You go, let's say I want to define f of x. I type in f of x, and then I put a colon, so control and the little bracket sign here just under delete. I put that in, and that equals x, so whatever the equation is, and it'll say done to say it's defined. So doing that will save me time in terms of like rewriting it on the CAS and all of that. So those are just 2 major tips that I would give you. Daily schedule in terms of revision and practice exams. So I prioritized subjects I was a bit weaker at. So for me, I wasn't as strong at my English subject. So that was something I struggled a little bit at. So I dedicated a lot more time for the subjects I was a bit weaker at. And the subjects I was stronger at, I didn't do as much practice. But the main thing is I tried to do a little bit of every subject every day. So whether it's just one difficult question or whether it's doing a whole practice exam. So try to do a little bit of every subject every single day. Daily schedule. So during the break between like school and exams, I was literally doing full-on practice exams, trying to like revise them, go through them in a lot of depth, and that helped a lot. But sometimes you just don't get the time. So pick out the hard questions, time yourself, and go through them. So that might also be really helpful. Managing time in exam 2. So for exam 2, yes, time management is hard. So again, like I said, use your CAS wisely, define them. Don't be too reliant on your notes because obviously if you're flipping through your notes, you are wasting your time. So don't be too reliant on that. And obviously use reading time wisely. So plan out your strategies. Are you going to do short answer first or would you rather do multiple choice first? So think about that. Going about the exam. So what I did was what I like to do during the exam that worked for me personally, it might not work for everyone. So I did the extended response first and I just rushed through it. So I wasn't too careful. I was just rushing through extended response, trying to get every question done. Then I went back to multi-choice, did the questions, and then I still would have some time left over. So I'd go back to those extended response and then sort of like go through them a bit slower and check my answers. But again, I have friends who did really well, who did multi first and then did short extended response. I know other people who just slowly worked on extended response and did multiple choice. And that might be sort of like a safety net because in multiple choice, you can guess your answers and still get them right. And it's a bit hard to do that in extended response. So again, that's the point of doing practice exams. You try all of these strategies and see what works best for you. Was it a strong interest? At the start, I did have to do a lot, and I was interested in like the maths topics, but I did find that there were some topics where I did have to do a lot of work to sort of get my head around it, especially circular functions, which I found extremely difficult in year 11. So, but again, you sort of like when you revise and you're doing those questions and you're like practicing regularly, it starts to sort of make sense again. How many practice exams did I do? So I did Methods 3-4 in year 11. So I did quite a few practice exams. I think I did about 10 to 15. But again, I was in year 11, and in retrospect, I don't think I needed to do that much. I think it's more important to figure out how you go over those exams and correct them rather than just mindlessly do a bunch of practice exams. What revision should we prioritize? What should we be doing? So again, if I were you, I would do a practice exam and see where you're losing marks. So your first practice exam, it can be discouraging, but if you specifically look for where you're losing marks, based on that, you can prioritize what you need to work on. So are there any particular topics that you might need to work on? Do you need to work on maybe using your CAS a bit more quickly, and that comes with practice. So that depends. Do a practice exam, see where you're going wrong, see where you're, a little bit confused. Do it without time and see how that is going. Oh, and during the swap back period, try to focus on practice exam questions. Probability questions that require 2 marks, again. Oh, yeah, that's awesome. I'll put that up if anyone wants to access, if that's an okay link. Okay, so for probability questions that can be done by CAS, require 2 marks. What's a method of working? So questions like that, you basically want to put whether it's binomial or normal distribution. So before, when we were going through probability, is it X and like that curly bracket, and then in brackets the number of trials and probability of success for binomial, or you can say whether it's normally distributed. So you can say N, the curly brackets, mean and variance. So that would be your working out, and then you just do it on the CAS, and that should get you your 2 marks because there's really nothing else you can do. How can you solve for X for 2 functions on the CAS? Yep, okay. So you go menu, algebra, solve. And if I just say I want to solve for sine X, so menu, algebra, solve, then I put sine of X, and then comma X. So that's how it should look. So hopefully you can see. Enter. Oop, I forgot to make it equal to. So I'll do sine of X equal to 0 and solve for X. So let's do a basic one. So it's equal to 0, solve for X, and it will come up with a general solution. You can just use the general solution and, specify, and like figure out all the solutions for that domain, or you can do given, so control equals, and you find a straight line, given, let's say 0 is greater than or equal to X, which is less than or equal to 2 pi. And that will give you specific solutions. So you can restrict the domain. Yay, nice. Interprets trig solutions on the CAS where it displays n. So n, so again, it's giving you a general solution. It's not giving you the actual solution. So if you want to interpret it, try to make it so that you either define the domain. So let's say you've got f of x and then define the domain, or you can just solve it yourself. So it's going to give you that general solution. Make n equals 1, n equals 2, n equals 0, and keep going until you just solve that solution, until you kind of meet your domain. Practice methods exam. So I think someone's put up a link. Personally, my school just gave like a bunch of practice exams from like different companies. You can always rely on the VCA exams. Another thing you can do is, if you want, you can get on Ed Unlimited. There's also practice exams in there, so you can try those out too. So plenty of resources. Yeah, so you can just have a look at all of those resources. Usually you don't. They don't take marks off. For trig solutions, yes, you do. But for that plus C for integrals, no, you don't. Will you always have 2 base angles? Nope, not for tan. If you have tan, you'll only have 1 base angle. Yeah, thank you for that, yes. The CAS marks, I think, yeah, exactly. That's absolutely correct. Perfect. Not so much. You need to say whether it's binomially distributed. So the one I just resolved, so you need to say whether it's binomially distributed. binomial, that little bracket thing, and the number of trials and probability of success, or whether it's normally distributed. So no, it won't be a method mark. So writing just the probability of x equals this is not necessarily a method mark. Limited number of lines. Yeah, so that's always a problem. What I do is I like to write on the left side, put an arrow to the top of the right side, continue there. If that doesn't work for you, you can always request extra paper to work on. Can we put? Yes, you can. If you want to, yeah, by all means, yes, you can. As long as it's bound, it's A4 maximum size, you can put whatever you want in there. And last question, for a function in terms of d, can you write the derivative? I think it's very unlikely that you would get a function in terms of d, but yes, it would be correct to write it as d by dd. Again, very, very unlikely to get something like that. So yep, that's it for the lecture today. Thank you all for tuning in, and sorry that it did run over time. All the best for your 3-4 methods exam, and I hope that you all go the way you want to.